Here's another example of projectile motion. Here we have a stone that's being projected at a cliff. It's being thrown up there. We see once you throw the stone, it's going to follow a parabolic path of projectile motion, and it's going to land up on top of the cliff. We want to know what the height of the cliff is, how fast the speed of the stone right as it hits impact, and the maximum height that it reaches as it goes. So this is another kinematics. This is a projectile motion, which is basically kinematics in 2 dimensions. And so what we're told is it has an initial speed of 42 meters per second. That initial speed is the magnitude of the initial velocity, and we're told that it's sent upward at an angle of 60 degrees. So between the magnitude of the initial velocity and the direction, we can have the full initial velocity vector available to us. We're told that the stone strikes 5.5 seconds after being thrown. That is going to be our time, the time of flight. And we want to know what the height of the cliff is and the speed just before it makes impact. So if we want to know what the height is, we know that we begin at the ground, and we know that we end up at the impact point. That is a displacement, a net displacement in the y direction that we're looking for. We also, we will find that first. So if we're talking about displacement in the y direction, and we know the initial velocity, we'll go ahead and start considering the y direction and the kinematics in the y direction. So if this is a projectile motion problem, then our acceleration in the y direction will be negative 9.8 meters per second squared. That's always the case as long as we're on Earth for kinematic equations. We know that the time of flight, the time that it's in the air, is 5.5 seconds. And we're given the initial velocity vector, but if we're talking about just the y direction, we need to look at the y component of that initial vector. And so the y component is going to be the magnitude, which is 42 meters per second, times the sine of the angle at which it's thrown, which in this case makes it 36.4 meters per second. And since it's thrown upward and to the right, that means that both our x and y components of the initial velocity should be positive. So we already have our 3 kinematic variables that we need to know, and what we're asked is if we want to know the height that it reaches, we want to know the displacement in the y direction. So in order to find that, we can already calculate it using a kinematic equation that has all these terms, does not have the final velocity in the y direction. And the equation that we use is this. For our acceleration, we use negative 9.8. When we add all this up, we end up with delta y is a positive 52 meters. So we end up 52 meters above where we began, which makes sense from the picture of what we're trying to find. So this is our answer to part A. The next thing we're being asked, after the height, is the speed of the stone just before impact. Now here, if we have motion in multiple directions, then the speed is the magnitude of the velocity. And so if you have your speed is the magnitude of your velocity, and your velocity has an x component and a y component. So here the speed is the magnitude, and it's found looking at the magnitude of the vector, which treats it like a right triangle, like the hypotenuse of a right triangle. So in order to find the speed at impact, we need to know the velocity at the in the y direction, and we need to know the velocity in the x direction. Well, we already have 3 kinematic variables, so we can find the velocity in the y direction with what we know right now. The velocity at impact is the initial velocity plus a times t. We know that t is 5 seconds. And our velocity is negative 17.5 meters per second. That makes sense, because that means that, number one, the negative sign means that we're going downwards, which we should be if we're looking at the velocity at impact. We should be going downwards in the y direction, and our magnitude is less than the initial amount because we're still up in the air. However, we also need to know the x component of the velocity. And we can find the x component of the velocity directly because we know the v0 vector. And so we know that the x component will be the magnitude of the initial velocity times the cosine of the launch angle. In this case, that will be 42 meters per second times the cosine of 60 degrees, meaning we have a x component of our velocity of 21 meters per second. And since this is projectile motion, we have no acceleration in the x direction. The initial component of the velocity in the horizontal direction will still be the same component, horizontal component of the velocity at the end, because there'll be no change. So in that case, the magnitude of the velocity, which is the speed, now it's a little bit more complicated because they're vectors instead of in the same direction. It's still an absolute value, but it has to be added in terms of vectors. Our speed will be 21 squared plus Vy is negative, but we're squaring the negative amount. These are as if they're sides of a triangle, so they count as positive as lengths, even though they're downward, even though they're negative. It just means that you're going downward. It doesn't make it anything different about the vector itself. And we see that the total magnitude is 27.3 meters per second. And so this is our answer to B. That's the total velocity, or beg your pardon, that's the total speed on impact. We found the final velocity in the y direction at impact. We found the velocity in the x direction, which is always constant. We added them as vectors to find the overall speed at impact. The final step is to find the maximum height h. We want to know the maximum height that our projectile will reach as it flies. And if we're talking about this height, which occurs at this point along the motion, the time that it takes for the object to go from the ground all the way to the end is 5.5, but there's no symmetry here, so we don't know how much of that 5.5 is going up and how much of that 5.5 is coming back down. So we can't use that time that we know for any calculation about this motion to go upwards. But if this is the maximum height is when you are not going upwards anymore. And if you're not going upwards anymore, that means that your velocity, your final velocity in the y direction, is equal to 0 because you're not going up anymore. But we also know that our acceleration in the y direction is still due to gravity. That hasn't changed. And the launch is the same as well. And so our initial velocity in the y direction is also the same as before. Because the acceleration is the same because we're on Earth, the launch is the same regardless of where we're measuring, whether measuring halfway through the flight or if we're measuring at the landing site. And so in this case, if we're talking about leaving the ground and going up to the peak spot, then the height reached is in fact the displacement during that part of the flight, going from the ground up to the very top. And so we can use another kinematic equation and find out what that peak height is. We find that delta y is 67.6 meters, which is the displacement up to where we stop moving in the y direction, which is the height, the top of the arc, and thus that is that capital H, the highest that we go.